Okay, so before starting to solve the problems, let's see some of the basic things we need to know about the predicate calculus. So, a predicate is like a function, for example, of x comma y takes two variables here and it returns always a boolean value. Okay, for example, let's assume it checks if x is equal to y, return true, return true. Okay, else return false. So this is an example of a predicate. It takes two values and gives the output as true or false. So remember, always the predicate will return true or false, and value of the predicate depends on the value of x and y, right? So what are the different values x and y can take? That's called the domain of x and y. Now let's see the important notations what we use in predicate calculus. One is for all x. For example, if I write for all x p of x, that means this predicate will evaluate true if p of x is true for all the values of x in the domain. Okay, for example, if uh, s is the domain and we have 1, 2, 3, 4, then the predicate for all x p of x will be true if p of 1 is true and p of 2 and p of 3 and p of 4. If all these are true, then we say that this predicate will evaluate true. And the another notation we use is there exists a p of x. This is equal to p of 1 or p of 2 or p of 3 or p of 4. So at least one of these values are true, then there exists p of x will evaluate to true. Okay, we will have a lot of questions related to converting an English sentence to predicate. So we should understand one thing. For example, let's assume you have a class and this is your domain and you have some boys and girls. So maybe I will say B1, G1, B2, G2, B3 and G3. Okay, so these are the students in the class, and let's assume you have a English statement. For example, uh, there exists, there exists, there exists at least one boy, he is happy. Okay, so this is the predicate. So it says in this class there exists at least one boy, he is happy. Okay, so let's assume boy of x is a predicate. If you give a student in this class, it will return true if it's a boy, if it returns false if it's a girl. And let's assume you have happy of x, happy of x. This will be returned true if the student is happy. Okay, so our predicate says there exists at least one boy is happy. So let's assume B1 is not happy and the girl G1 is happy, B2 is also happy, and others are, let's assume, happy and unhappy. Okay, now I can write this sentence as there exists. See, remember this. There exists means you'll use this notation. There exists an x. Okay, from this domain we have boy of x. He is a boy and he is happy, right? So that's the meaning. There exists at least one boy. He is happy means he is a boy and he is happy. So and happy. Okay, so this is the statement that actually represents there exists a boy in this class, he is happy. Okay, so remember this, we are actually so we are using the boy of x and see this and, okay, and happy of x. So that's a one property of boy, so we are using and to connect these two. Okay, now what happens if I give this domain to this predicate, it should evaluate true, right? So we'll give first b1, it's a boy of x, that is true, and he is not happy. So if I give b1, this will evaluate true, but I had to give all the elements. Okay, so I'll give g1, boy of x is false because it's a girl, So again, for G1 this will evaluate to false. Then I will give B2. For B2, boy of X is true and he is happy, right? He is happy. So at that time this is going to evaluate true. So you don't need to worry about the other elements because you have got at least one person. He's a boy and he's happy, right? Now let's assume there's another statement that says all the boys in the class are happy. Okay, are happy. Okay, so this is the statement, and let's assume we have all the boys, they are actually happy. So my predicate should evaluate to true. So let's assume I'm using for all x. Okay, because I have all the boys, see, all the boys I have to use for all x in this domain. Let's assume I'm writing boy of x and happy of x. Now what happens? So see here I'm using boy of x and happy of x. So I'm giving b1. B1 is boy of x, that is true, and happy of x, that's also true. So for b1 this is evaluating to true, this portion is evaluating to true, right? Now if I give g1, right, for all the elements it should be evaluating to true, right? For g1 boy of x is false, right? So that means for g1 this function that is basically going to evaluate as false, but we know that this statement should be true, right? So that means we have to give for all x boy of x implies happy. Okay, so I don't need to worry about girls. So when I give b1 this will evaluate to true, then true, and it's also happy, so that's fine. Then I give g1 boy of x will evaluate to false, and false implies anything is true. So for g1 also this is going to evaluate as true, for b2 also this is going to evaluate as true. Okay, so remember this, whenever you have all x, then the property here happy will be connected by implication. Okay, and whenever you have there exists an x, then this property will be connected with and. Okay, also note that we know that for example there exists a boy, he is happy can be written as there exists an x, boy of x and happy of x, right? So one thing we should know that if I do 2 times negation, this will be the same statement, right? If I do 2 times negation. So let me do this. Take this negation inside. So that will be for all x negation, right? Boy of x and happy of x. Okay. Now negation for all x. See, I have boy of x and happy of x. So if I negate this, this will be equal to not boy of x or not happy of x. Then I can write for all x. This I can write as boy of x implies not happy of x. Right, so this is also equal to there exists an x, boy of x and happy of x. Okay, so remember this because it says that this person says that there exists a boy in this class, he is happy, right? So he says it is not the case that all the boys in the class are not happy, right? It's not the case that all the boys in the class are not happy. That means there exists at least one boy, he is happy. Similarly, if I say all the boys in the class are happy, I can write it as for all x, boy of x implies happy of x, right? So I can write it as for all x, and this is p implies q form, so I can write it as not boy of x or happy of x. This is true. Okay, so these two statements are same. Okay, if I take all the persons in the class, if he is not a boy, then it's okay. If it's a boy, then he should be happy. So these two statements are the same. I can even rewrite this as, for example, I can do 2 times negation of this statement. So for all x, this will be equal to not boy of x or happy of x, right? Then I can take the negation inside, so that will be not all x, sorry, so that will be not the existence x, not, here I have not boy of x or happy of x, right? So that will be equal to not the existence x, boy of x and happy of x, sorry, not happy of x. Okay, so this is also true. Okay, so remember this, I can rewrite this sentence as, either I can write it as for all x, not boy of x or happy of x. This is true. These two statements are same, or I can write not, it is not the case that there exists a boy of x and he is not happy. Okay, so that means all the boys are happy, right? So these three statements are equal. Okay, what is the correct translation of the following statement into mathematical logic? Some real numbers are rational. See, if you see, we have some functions here. So real of x will be true if the number is real. Similarly, rational of x will be true if that number is rational. Okay, so we have the sentence with some real numbers. See, some real numbers, that means there exists an x. Okay, then it's a real number and and it is rational, right? Ration of x. Okay, so remember this, whenever we have some, that is there exists an x, then we'll associate the property with and. If you have all, then we will associate the property with implication. Okay, so here I have to use and, so the answer should be there exists a real of x and rational of x, so the answer should be C. So we have again a English statement here. It says none of my friends are perfect. That means all of my all of my friends are not perfect, right? So I have two predicates here. F of x means friend of x and p of x means perfect. So all of my friends are not perfect should be written as for all x, right? If it's a friend of x implies, see, whenever I am having all of x, I have this implies. Okay, f of x implies not p of x, right? So I had to find out here. If I see the choice, everything is there exists an x. Okay, so maybe I will see what it is. So here I have f of x implies not p of x, that will be equal to f complement x plus not p of x, not p of x, right? So I know that a bar plus b bar will be equal to ab all bar. So I can write this as for all x not f of x and p of x, right? So I can take the not outside. So when I take not this side, this will be not the existent x, right? F of x and p of x. Okay, so that will be the answer D. Not all rainy days are cold, right? That means there exists at least one rainy day which is not cold, right? So I had tried there exists a day D which is rainy, right? Rainy day. So rainy of day is true and see, because there exists, I am using and, which is not called, right? Not called. So the answer should be D. Not all that glitters is gold. See here, you should not take the literal meaning of this. You should take the poetic meaning of this statement. The statement says, "Not all that glitters is called gold." That means there exists at least one glitter which is not gold, right? Which is not gold. So I have said there exists an X such that it is a glitter, right? And it is not gold. See, I am using there exists and. Okay, so this should be the answer. If you see, the answer should be D. Which of the following first order logic sentence does not represent the statement? Not every graph is connected. That means there exists at least one graph which is not connected, right? So I can directly say that choice D is false, right? Because it says for all x, if x is a graph, then it is not connected. That is not true, right? There exist graphs which are connected also, right? So the choice D is false. So the answer should be D. Anyway, let's evaluate the other sentences. So it says not every graph is connected. That means there exist some graphs which is not connected, right? So the predicate logic formula should be there exists an x, right? It is a graph and it is not connected. So the choice B is correct. Now I have, if you see the choice A and C, I have the answers in universal quantifier, right? So let me write what A is. A says for not all x, x implies connected. We know that it is true, right? It is not the case that all graphs are connected. That means there exists at least one graph which is not connected. Anyway, let's try this. Let's take the negation inside. So we'll have there exists an x, not x implies connected of x is not of x, right? Plus connected of x, right? That will be equal to the exists an x. By I can use the De Morgan's law here, right? So that will be equal to x and not connected of x. So this is the same expression as here. Now let's see the choice C. It says not all x, not x or connected of x. So I can take the negation instead. There will be the exists an x, right? Not x or connected of x. That will be equal to the exists an x and not connected of x, right? See, I'm just applying the negation to both x and connected of x. So this is same as what we have got here. So all these three statements A, B, C are same and D is false. Okay. So the answer should be D. Tigers and lions attack if they are hungry or threatened. Right. So what it means is all tigers and lions attack if they are hungry or threatened. So it should start with for all x. Okay. So the meaning is all tigers and lions attack if they are hungry or threatened. Now inside this, if you see tiger of x and lion of x, so that actually corresponds to the literal meaning of this statement, right? But do you think this portion ever evaluates to true? No, right? Because you cannot have an animal, that is actually a tiger as well as lion, right? So tiger of x and lion of x is always going to evaluate as false. Remember this, okay? So basically this means for all tigers or all lions attack, right? So basically this is tiger or lion attack, right? So we have to read this as tigers or lions attack. So it should be tiger of x or lion of x. So choice A should be wrong. Now, for all tiger of x or lion of x, once you have all x, you should have implies, right? So if you see all choices, we have implies. Now, what we are saying, if they are hungry or threatened, if they are hungry or threatened, then they will attack, right? So we have a statement just after the if that says hungry or threatened, then that means implies attacks, right? So that means this choice is wrong. This choice is wrong. So the correct option should be D. It says it's a tiger or lion, and if it's hungry or threatened, then it will attack, right? So answer should be D. Identify the correct translation into logical notation of the following assertion. Some boys in the class are taller than all the girls. So we have some boys, right? That means there exists an X, boy of X, and since I have there exists an X, definitely this should be and, right? Boy of X, they are taller than all the girls, right? So if I have girl of X for all Y, sorry, girls, right? So for all Y, see, girl of Y is true. See, remember, if I have all the Y, then it should be an implication, right? Then I have taller of X comma Y. So the answer should be D. Which one of the following is the most appropriate logical formula to represent the statement gold and silver ornaments are precious? Okay, so what it means is all the gold and silver ornaments are precious. Okay, so we have to start with all x. Now it's given that g of x is gold ornament and s of x is silver ornament, right? So we have to say gold ornament and silver ornaments. We cannot say when an ornament is gold as well as silver, right? As well as silver, right? So it should be actually all the gold as well as all the silver ornaments are precious, right? So g of x or silver of x, that means it should be precious. Remember this, for all x we have implication here, okay? So the answer should be D. So let's see the next quantifiers. So sometimes it is better if you can visualize that as a program, then it will be somewhat easy to visualize what's happening when you have a nested quantifier. So first let's see how can we represent for all x p of x in the form of a program. So let's assume you have a function that's going to evaluate for all x p of x. So that should be returning a boolean value, right? And let's assume its name is f1. So we can write for every x in the domain, okay, if not p of x, that means if p of x is false, return false, okay, and finally you return true. So this could be the program representing for all x p of x. So what we are basically doing is we are taking the element from the domain one by one, and whenever this p of x is evaluated as false, we'll immediately return it as false. We don't need to proceed. Okay. If all the values are true, then we will return true. Okay. Now, if you see there exists an x p of x, if this is your program, you can say that same function. Let's assume f1 for every x in the domain. If p of x, that means if you have at least one value that is true, then you can return here true. Okay, otherwise you can return false. So this function will be representing there exists an x p of x. Okay, because for every x in the domain, if you have at least one value that is true, then you can immediately return true. You don't need to evaluate the other elements. If you can get at least one element, you can stop there and return true, right? Now let's see for all x, all y. Let's assume you have p of x comma y. Okay, so that this means that you have a Boolean function, then you have, maybe I will just erase this. So you have a Boolean function f1, okay, and it says for every x in the domain, okay, then for every y in the domain, okay, for every x in the domain, for every y in the domain, if not of p of xy, that means if p of xy is false, return false, okay, otherwise you can return true. Okay, so maybe I will explain this with some elements. Let's assume your domain is for both x and y are 1, 2, 3, 4. Then what happens? You fix the value of x. See here, first you have x, so you select one value for x, that's 1. Then for every y, okay, so you are basically checking y starts from 1 to 4, right? So 1, 1, 1, 2, 1, 3, and 1, 4, okay. Then you are changing the, then you are taking the next x. Next x will be 2, so you will be checking 2, 1, 2, 2, 2, 3, 2, 4. Then you have 3, 1, 3, 2, 3, 3, 3, 4. Then you have 4, 1, 4, 2, 4, 3, and 4, 4. Okay. So for all this space, if your domain is 1, 2, 3, 4, if all this space in this order, see I am taking the pairs in this order, okay, in this order, okay, always I am selecting in this order, okay. If I evaluate all these values to true, then this function will be returned as true, okay. So let's see for all x, what is the meaning of for all x there exists a y p of x comma y. What it means? You take an x, so it's again two for loops. So you take an x, so for example you take x is equal to 1, then you loop through all the y, that means this first row, okay. In this first row you should get at least one pair as true, okay, and then you will come to the next row, again you need to get at least one pair as true in this row. Again you come to the third row, you have to get at least one from here. That means all the x, see all the x, maybe here it is true and here it is true and this one is true and this one is true, let's assume. So that means for all the x, for example x is equal to 1, there exists at least one y, that is 2. So 1, 2 pair is selected. Now for the second x, that is 2, there exists at least one 5, that is 4. Third row, if you see, for all x, right, at least one y, that is 3, 1, and next is 4, 4. So if you see all x, right, for all the values of x, there exists at least one y which is true. That is the meaning of this one, okay. Now if I have there exists an x for all y p of x comma y, it means there exists an x. So for example, if I take x is this one, then for all y p of xy should be true. That means this row completely is true, okay. Or since it's there exists an x, or this row is completely true, or this row is completely true, or this row is completely true. So out of these 4 rows, at least one row should be completely true for this state. Is that clear to everyone? Okay. So remember this, for all x, all y, every pair should be true. For all x, there exists a y. That means every row, at least one pair should be true. There exists an x for all y. That means there exists at least one row which is fully true. Okay. Now let's solve some problems. What is the first order predicate calculus statement? Equivalent to the following. Every teacher is liked by some student. So I know that it should be all teachers, right? So it should start with all x. Then teacher of x implies, right? That should be the way we should be writing for all x. Teacher of x implies, right? So that means the choice D is wrong. Then by some student, that means student of y and, right? So that means choice A should be wrong. So the answer should be B or C. Now if you see, you know the answer B is correct, right? For all x, teacher of x implies there exists a y, student of y, and xy comma x. So this should be right. Let's see. Anyway, the choice C, it says there exists a y for all x. So what happens is, let's assume y is a student and x is a teacher. Okay, so what it says is there exists a y. That means you are selecting the student first, and then you are saying for all x. That means this student, the exists a student, he likes all the teachers, right? Basically, it says there exists a student, right? You are fixing the student first. Okay, there exists at least one student for all x. Then you are actually looping through all the x. So basically, if you have something like this, what we are doing is basically you are actually fixing the y. For example, let's fix the y, this one. Okay, then you are saying that for all x, that means this column. Okay, so let's assume the pair is x comma y. Then you are saying you are fixing the y and selecting all the x's. Okay, and you're saying that there exists one student, he likes all the teachers. That is not the statement. It says every teacher is liked by some student, right? So the answer should be B. Which one of the following is equivalent to this expression, right? So let me start with D, because what I know is not of all x is equal to the exists x, and not of the exists y is equal to all y, right? So most probably D and this expression may be same. So let me try that first. So I can take this negation inside. So this will be the exists x. This will be for all y, right? Then I have negation of a of x comma y or b of x comma y. So just let me write it as a plus b implies c, right? So this will be equal to a plus b all bar plus c, right? So that will be equal to a bar into b bar plus c. Now I have a negation, right? So that negation, if I apply, this will be equal to a bar dot b bar all bar plus c bar. So that will be equal to a plus, so that will be equal to a plus b plus c bar, right? So this is not equal to ab plus a b c bar, right? So that's not the case here. So that means maybe I should try c. C is also same thing, right? So here I have the exists an x for all y. Then I have the negation. Here I have a b implies c, right? So I can write it as this portion. I can write it as ab all bar plus c. So that's equal to a bar into, sorry, a bar plus b bar plus c. Now I have the negation. So that will be like this, right? So that will be equal to a into b into c, sorry, c bar, right? So I can write it as the exists an x for all y, right? A of x comma y and b of x comma y and not c of x comma y, right? So that should be equal to this one. So the answer should be C. Which of the above statements are equivalent, right? So for not all x p of x will be equal to there exists an x not p of x. So that means 1 and 4 are equivalent. So the answer should be B, right? Anyway, let's see the second choice. It says not all x p of x. Sorry, not there exists an x p of x. That means for all x not p of x. And here this means for all x p of x, right? So these two are not equal to this one. So the answer should be B.
Which of the following first order logic statements represent the following? Each finite state automation has an equivalent pushdown automation. So basically the statement says for every finite state automation, there exists an equivalent pushdown automation, right? So we have say for all x, if it's a finite state machine, that means FSA of x, right? Implies. So if you have all x, definitely you should have implies. Then that means there exists a PDA y, right? So we have there exists, then you should have and here. So there exists a PDA y and it should be equivalent, right? Equivalent of x comma y. So this should be the statement. So if you see the answers, A should be the correct answer. Suppose the predicate f of x comma y comma t is used to represent the statement that person x can fool person y at time t, right? So which one of the following statements below express the best meaning of the formula? So we have a formula here and four choices here. So if you see, we have a note here. So I can take this into left side. So that will be equal to not the exists an x for all y for all t f of x comma y comma t, right? So it says that it is not the case that there exists someone who can fool everyone every time, right? So that means no one can fool all the persons all the time, right? So that means no one can fool everyone all the time. The answer should be B. Given three positive integers x, y, and z, and a predicate p of x. So this is the predicate, and we had four choices. So it's given that x should not be equal to 1, and you are passing x to this predicate, right? So if for all y, there exists a set such that x is equal to y into z, that implies y is equal to x or y equal to 1, right? So if this portion is true, this portion should be true, right? That is the meaning of this predicate, right? That means if you can factorize x into y into z, then y should be equal to x or y should be equal to 1. So this is the definition of prime number. So answer should be A, right? So anyway, let's see an example. Let's see what happens on P of 4. So if it evaluates true, then choice A should be wrong, right? Anyway, let's see what happens on P of 4. So we have set of integers 1, 2, 3, 4, etc. And we are going to calculate P of 4. Right? So x is not equal to 1 here. So P of 4, this portion will be valid to true always. Okay. Now let's come to the next portion. For all y, so we start from y is equal to 1. There exists a z. So y such that x is equal to y into z, right? So z should be 4, right? Then only 1 into 4 will be equal to x, right? In that case, y is equal to x or y is equal to 1. So y is equal to 1. So this is true. So when y is equal to 1, this is evaluates to true. Then y is equal to 2. Let's see what happens when y is equal to 2, right? So when y is equal to 2, z also will be equal to 2 because y into z should be equal to x, right? So 2 into 2 is equal to 4. So that means this portion is true, right? Now y is equal to x. No, y is not equal to x, right? Because y is equal to 2 now and our x is equal to 4. Y is equal to 1? No, y is equal not equal to 1, y is equal to 2. So basically for P of 4, when y is equal to 1, sorry. So for P of 4, when y is equal to 2, this expression actually evaluates to false. That means P of 4 is evaluated as false, right? So the second statement, P of x being 2 means x is a number other than 1. This is wrong. P of x always evaluates to true irrespective of the value of x. That is also wrong. P of x is true means that x has exactly two factors other than 1 and x. This is also false, right? You can see this by just by giving, for example, P of x is equal to 5. This will evaluate true. So this statement says P of x is true means x has exactly two factors other than 1 and x. But we know that we have only two factors, that is 1 and 5, right? So if you give P of x is equal to y, this expression value is true. So this choice is also wrong. So the correct option is A. You can just see it by this predicate. This is the definition of prime number. Which one of the following is not logically equivalent to this predicate, right? So this predicate is not there exists an x for all y alpha and for all z beta, right? So we can take this not inside, so that will be equal to for all x not for all y alpha and for all z beta. So that will be equal to for all x. I can take this not inside, so that will be equal to for all y alpha and for all z beta all formula, right? That will be equal to for all x not for all y alpha or not for all z beta, right? So that will be equal to for all x. This I can write it as for all y alpha implies for all not all z beta, right? Okay, so that's equal to for all x all y alpha implies there exists a z not beta, right? So that means choice C is also equivalent to this expression. If you see here, I can write for all x, right? This is an OR. So A or B will be equal to B or A, right? So I can write it as for all Z beta or not all Y alpha, right? This I can write it as for all x. This can be written as for all Z beta implies this can be written as there exists a Y not alpha, right? So that means choice B is also true. So both B and C were correct, but you cannot convert this expression to A or D. So both are not equivalent. So here marks are given to all in the exam. So the answer is actually both A and B.
Which of the following predicate not represents the below phrase? If anyone cheats, then everyone suffers. So let's assume you have a domain got x1, x2, and x3. So it says if anyone cheats, remember this, there is an if here, okay? If anyone cheats, so let's assume cheat of x denotes x is a cheat or not. So it says cheat of x or cheat of cheat of x1 or cheat of x2 or cheat of x3. So if this is true, any of this is true, then that means everyone is going to suffer, right? So that means suffers of y1 and suffers of y2 and suffers of y3, right? So you can represent this as there exists an x, cheat of x implies for all y suffers of y, right? So this statement is direct predicate that basically represents the statement if anyone cheats then everyone suffers, right? But we have this here the predicate in all x format, right? So note that this is not equal to there exists an x, cheat of x implies for all y suffers of y. Okay, these are different statement. You have to see the bracket here. Okay, this statement, for example, let's assume there is x1 is not a cheater. So here, if you come right, so it just takes cheat of x, that is false. So false implies anything will be true, and we need only one true because there exists an x, right? So if x1 is not a cheater, basically we are not at all worried about other uh, persons, right? So this is not the correct statement. This statement is correct. It says if there exists a cheat person, then everyone suffers. Now let's see the predicate Q1 and Q2. So let's assume you have a predicate. Okay. Now you take one value and you see this predicate should evaluate to true, checking this place basically this statement, right? If for example, if I give that x1 here, it should check if x1 is a cheater or not first. If x1 is not a cheater, then it's done, right? So if x1 is not a cheater, then I don't need to worry, right? So let's assume x1 is not a cheater. So you're just checking not a cheater of x1, then it's okay, right? Then you see x2. Let's assume is a cheater. So for x2, so this also I am going to evaluate every value in this domain. I am going to evaluate, right? So let's say and so cheat of not cheat of x1, that's fine. And let's assume x2 is a cheater. Then what I will do? So I am just calculating not of cheat of x, that will be false now. So if it is false, then what should I do? Then I should evaluate that suffers of x1 and suffers of x2 and suffers of x3 should be true, right? So basically what I am doing is, okay, I will just finish this. Let's assume x3 is also uh, not a cheater, or you can assume it's a cheater. So let's assume x3 is a cheat. Then I am seeing and not cheat of x3 or suffers of x1 and suffers of x2 and suffers of x3, right? So basically what I want to say is when I'm getting a predicate, I am just checking is a cheat or not, right? So cheat of x1 not. So this will be true if he is not a cheater, right? If this will be false if he is a cheater. So if he is false, so I can say then that means suffers of y1, right? And suffers of y2 and suffers of y3, right? Sorry, suffers of x1, it's x1, right? X1 suffers of x2 and suffers of x3, right? So for each element in this domain, this particular expression should be true. For each value in this domain, this particular expression should be true, right? So for example, I am just taking x1, x2, x3, and let's assume all are not cheaters, right? So not cheat of x1, that will be true, not cheat of x2, that will be true, and not cheat of x3, that will be true. So none of them are cheaters. That also means that for this domain, right, this predicate should be valued as true. And let's assume you have x1, x2, x3, and x4, and let's assume x2 and x4 are cheaters, and x1 and x2 are good persons. So you take x1 and see is not cheat of x1, that is true, so you don't need to worry. You take x2 and not cheat of x2 is false because he is a cheater. That means this if I give x2, this predicate will evaluate as true only if everyone suffers, right? So I can write this as for all x, right? Not cheat of x1 implies this one, right? So I can say cheat of x1 implies for all y suffers of y, right? So that means the Q1 predicate is also true. It says for all x, if cheat of x1 is true, then everyone suffers. So now if you see these two statements, basically these two statements are same. You can take this all y to here also, right? I can take this all y here. The meaning of the statement will not change, right? So here it says for all x, all y. If cheat of x is true, then suffers of y. So I can take the all y side. The meaning will not change. So basically, both this q1 and q2 are represented in this statement. So here it is asked to find out not represent. So the answer should be D. Also, you should understand that we have used an implication with the exist because you have a if here. Okay, so far in the expression we were just saying there exists a rational number, but here if you see if anyone cheats, so there is an if here. Okay, so this particular statement basically should evaluate to true even for a null set. Okay, remember this, even for a null set this particular uh, statement should evaluate to true, or you can have a domain where all the values, all the persons are not cheaters. In that case also, this expression values true. So that means you cannot say there exists a person if he is cheater then everyone suffers, right? It's not like that. Okay. So there is a if here. Remember this if here, and then we are saying anyone cheats then everyone suffers. Okay. Now let's see what we mean by model. So model is a domain for which my predicate is true. For example, let's take the predicate saying that all boys are smart. So I can represent this predicate as for all x, boy of x implies smart of x. Okay, so this is the predicate. Okay, so you can have different domain for which this predicate evaluates true, right? For example, let's assume you can have a domain where you have two girls G1, G2, and two boys B1, B2, and let's assume B1 is smart as well as B2 is smart, right? For this domain, this predicate evaluates to true, right? Because if it's a boy of x, if it's a girl, I don't care. If it's a boy, then he should be smart. So this is a valid predicate model, right? Or valid predicate domain, right? For this domain, my predicate is true. So I will say that this is a model. So I can have different models. So this is a model, example of a model. Now I can even have a class. Let's assume you have B1 and B2 and both are smart, right? Both are smart. If you see for this model also, this predicate evaluates true, right? So I can have maybe only one boy. This is my domain. This one boy, and let's assume he's smart. For this domain also, this predicate is true. Or even I can have a null set, right? and there is no boy here. This is just a null set with 0 elements, right? So in that case also you can have a model that actually evaluates this predicate to true. Okay, so remember this, whenever you have for all x, you can actually remove the elements from the model one by one, maybe till 5, right? Now let's see, uh, if I'm saying there exists at least one boy in the class, he is smart. Okay, so I'm saying at least one boy, he is smart. So there exists an x, boy of x, and smart of x, right? So if I take this as the domain, for this domain, this expression evaluates true, right? Because I need at least one, that is true here, right? For this one also, this predicate evaluates true. For this set also, this predicate evaluates true, but for this set, this predicate evaluates false, because I need to have at least one element inside this set to say that I have boy of x and smart of x. So remember this, whenever you have the exists an x, you need to have at least one element in this domain. Okay, here for all x, it can be 5. Now let's solve some questions related to this. Consider the first order logic sentence. So we have a first order predicate formula here. And it's given that suppose this predicate formula phi has a model with a universe containing 7 elements. Right? So we have a domain which contains 7 elements. Right? And for this domain, this predicate evaluates true. Now, if there exists x in this predicate, right? Then you can take this size of this domain to 5, right? Because as we know that for all x, all y, all v, all w, all x, all y, basically you can uh, remove the elements and make it 5, right? But if it has there exists, right? You know that you need to have at least one element inside the set, right? So here if you see there exists an S. So let's assume S, T and U are different. So let's assume S is not equal to T and this is not equal to U. Then that means your domain must have at least 3 elements, right? If S is not equal to T and it's not equal to U, right? But if S is equal to T, then you can have your domain to have 2 elements. If S is equal to T is equal to U, then you will have a model of one element, right? So if you see the choice A, it says there exists at least one model of phi with universe of size less than or equal to 3. This is true because it can be 3, right? Or it can be less than 3 also. So choice A is true. B says there is no model of phi with universe less than or equal to 3. This is wrong, right? You can have 3 or less than 3 depending on the value of S and T and U. There exists no model of phi with universe of size greater than 7. This is definitely wrong because already you have a model with 7. You can actually extend that, right? Every model of phi has universe of size equal to 7. This is wrong. You can have a model less than 7 also, right? So correct option is A.
Now let's see problems related to validity of predicate statement. So, given a predicate statement, we say it is valid if that predicate always evaluates the true regardless of the domain. So, whatever may be the domain, the predicate should always evaluate the true. So, that is the idea. So, if you have a predicate involving implication, for example, if you have P implies Q, so we know that this predicate will evaluate to false whenever you have true implies false, right? So this is the idea we are going to use for the next set of questions. P of x and Q of x be arbitrary predicates which of the following statement is always true? Okay. So what we know is we say predicate is valid. For example, if you take the choice A, we have for all x p of x or q of x implies for all x p of x or for all x q of x, right? So we say that this predicate is valid if in any domain, if you can assign the truth values from that domain, right? This predicate should evaluate to true always, right? So the idea is we have to select a domain. Okay, so you can select any domain as far as you are able to prove that this predicate is false. So I'm just taking a domain with two variables x1 and x2, and let me assign p of x1 is equal to false, q of x1 is equal to true, p of x2 is equal to true, and q of x2 is equal to false. See, my idea is I have to prove that this truth assignment should make this left side true and right side false, right? So how can I make the right side false? For all x, p of x should be false. So that's why actually I given for the p of x1 and x2 I given at least one value as false, so that I know for all x, p of x will be false. Or similarly for all x, q of x, I have given one value as false, so this also will evaluate to false. Right? So right side I have false. Now using the same assignment, if I am able to prove that the left side is true, then I can say that the choice A is false, right? Because I can prove that I have a truth assignment such that true implies false. Right? Now if you see the left hand side, for all x, that is first value of x will be x1, right? So p of x1 or q of x1, that is these two values, right? So that is true. Now next is x2. So p of x2 or q of x2, that is also true. So I have left side true and right side false. That means choice A is wrong. See, you have to select this assignment or you have to find this assignment. Okay, that is the important thing. Okay. Now let's see the choice C. We have for all x p of x implies for all x p of x, right? All implies for all x p of x implies q of x, right? So this is the right hand side. So if this predicate is not valid, that means we have a truth assignment such that the left hand side will be true and the right hand side should be false, right? So this side should be false means there exists some value for x that p of x is true and p of x is false, right? So maybe I will say p of x1 is equal to true and q of x1 is equal to false. Similarly, p of x2 is equal to false and q of x2 is equal to false. Okay. Now I know that for all x, p of x implies p of x will be false, right? Also, I know that for all x, p of x will be false, and for all x, p of x will be false because I have assigned p of x2 is equal to false, right? So for all x, p of x will be false. For all x, p of x will be false. False implies false is true. So basically, for this truth assignment, from this domain x1, x2, I have a truth assignment such that left hand side is true and right hand side is false. So that means choice C is also wrong. Okay. See the choice D. We have for all x, p of x by implication for all x, q of x, right? All implies for all x, p of x by implication q of x. So basically, I have to prove this side is true and this side is false. right? So again, see, I can make this false. For example, P of x1 is false, then Q of x1 should be true, or vice versa, right? So I can select, for example, P of x1 is equal to true, and Q of x1 is equal to false. Then P of x2 will be, I can take false, and Q of x2, I can take it as false. Okay. See, basically, I want to make this side true. That's why I'm taking this as false. Okay. So if you see P of x, by implication, P of x is false because I have true for x1 and Q of x1 is false. So this side is false. Now, if you see this one, left hand side, you have for all x P of x, for all x P of x, that is false, right? False by implication. For all x P of x, that's also false. So false by implication false will be true. So I have a truth assignment such that true implies false. So that means choice D is also wrong. So the correct option should be B. Anyway, let's see whether we can break B also. So choice B says for all x, P of x implies Q of x implies for all x, P of x implies for all x, Q of x. Okay, so if this statement is not valid, that means I have a truth assignment such that the left hand side is true and right hand side is false, right? So again, let's assume our domain S is equal to x1 comma x2. So this side should be false, right? So that means for all x p of x should be true and for all x p of x should be false, right? That means I need to have p of x1 is equal to true and p of x2 is equal to true and q of x, right? At least one value should be false. So I'm making q of x1 is false and q of x2 is equal to false. I know now right hand side is false. Now let's see whether with the same assignment I can make the left hand side true, right? So p of x1 that is true, that implies q of x1 also should be true, but here it is false. So with this assignment I cannot make the left hand side true, the left hand side will be false. Actually, there is no such assignment that makes the left hand side true and right hand side false. So that is the reason we'll have the answer B. Which one of these first order logic formula is valid? We have four choices. So let's see the choices one by one. Let's take the first choice A. We have for all x, P of x implies Q of x, right? All implies for all x, P of x implies for all x, Q of x, right? So to prove that this predicate is not valid, we have to have a truth assignment such that the left hand side evaluates to true and the right hand side evaluates to false. If you see the right hand side, we have for all x p of x implies for all x p of x, right? That means for all x p of x, how can we have this right hand side false? If we have true implies false, right? So that means for all x p of x is true. For all x p of x should be true, right? And for all x p of x should be false. So what we know is that if you in our domain, if you have x1, x2, etc., some number of elements, then p of x1 will be equal to true, p of x2 will be equal to true, and p of x3 will be equal to true, and so on, right? And what about q of x? Q of x can take any value apart from at least one of the q of x should be false because we have true implies false, right? So, for example, q of x1 can be false, q of x2 can be true, q of x3 can be true, but at least one value should be false. Now, if you see the left hand side, because here we have p of x implies q of x, and we already know that for all x p of x is true, this value p of this value is always going to evaluate as true, right? Now, if you want this value to have the truth assignment of true, that means always q of x also should be true, right? Otherwise, we cannot have this truth assignment as true, right? Here, because already we have assumed that for all x p of x is true, so that means this portion will be false. So you cannot make this assignment to true implies false. So ideally, the choice A should be true. Okay. Let's see the second choice B. It says the exists an x p of x or q of x implies the exists an x p of x implies the exists an x q of x. Right now, if this is not a valid predicate, so you should be able to prove that we have true implies false. So that means this portion should be false, right? So that means there exists x p of x should be true, and there exists an x q of x. This portion should be false, right? So that means all the q of x values should be false, right? So if you have q of x1, that should be false. Q of x2, that should be false, right? In P of x, you can have, for example, P of x1 is equal to true, and P of x2 can be true, right? P of x2 also can be true. Now, in that way, you can make the right hand side false with this assignment. You can make the right hand side false. Now, if you see the left hand side, we have P of x or Q of x. That means P of x1 or Q of x1. That is true, right? Similarly, we have P of x2 or Q of x2. That's also true. So, with this assignment, we can make the left hand side true and right hand side false. So, choice B is wrong. Now, let's see the choice C. We have the existence x P of x and Q of x by implication. There exists an x P of x and there exists an x Q of x. So remember, we have a by implication here. That means if the left hand side is true, the right hand side also should be true. If the left hand side is false, the right hand side also should be false. So if you can prove the left hand side is true and right hand side is false, then this is not a valid set. Or if you can prove the left hand side false and the right hand side true, then only this is not a valid set. So let's try make this side true and side false. So I had to make this side true, right? That means at least one of the x and one of the p of x and one of the q of x should be true. So let me make p of x1 is equal to true and p of x2 is equal to false. Q of x1 is equal to false and q of x2 is equal to true. Right? So if you see the exists a p of x, that is this portion, that's true, and the exists a q of x, that is this portion, that's also true. So the right hand side is true. Now, if you see the left hand side, with the same assignment, actually we should evaluate this to be true, right? Then only we can say that this relation actually holds, right? If I can prove that the left hand side is false, then this is not a valid argument, right? Now, if you see the same assignment, P of x and Q of x, that is true, false, that is false, false, true, that is also false. So the left hand side we have false and right hand side we have true. So that means choice C is also wrong. Now let's see the choice D. It's straightforward. This is actually a wrong statement. Anyway, it says for all x there exists a y p of x, right? So let me write that. So let's assume you have 1, comma 2, comma 3 elements in your domain. I will just explain this so that you will be able to understand this perfectly fine. So we have the pairs 1, 1, 1, 2, and 1, 3. Then 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, and 3. Okay. Now I have to prove that I have a truth assignment such that the left hand side is true and the right hand side is false. So what it says in left hand side for all x, that means all the in all the rows, right? So the first element is x. So in all the rows, I have at least one y. So let's assume I have one is two, two three is two, and three two is two, and all other values are false. So in this assignment, the left hand side, if you see this left hand side, evaluates two, right? That means for all x, at least their x is one y. Now, if you see the second statement, it says that if the left hand side is true, the right hand side also should be true, right? That is what it means. Now, if you see the second statement, it says there exists a y for all x. So that means if you see the y, that is the second element. So you are fixing the y, and then you are actually changing the x. That means if the left hand side is true, then the right hand side, if you are seeing, it is looking to the column. Okay, it says at least all the elements in the one column is true. That is not the case, right? Here, if you see only one element here is true, and here also only one element is true, and here also only one element is true. But this statement says that all the elements in at least one column should be true. So that's also false. So choice D is false. So the correct answer should be A.
Which of the following predicate calculus statement is valid? So it's a very simple question. You can easily see that the choice A is correct. For example, if you see this is for all x p of x or for all x q of x, right? So this portion will be true if all p of x is true or all q of x is true. So we are sure that p of x, let's assume p of x is true for all the x, then for all x p of x or q of x also always will be true, right? So we cannot have a situation like true implies false, and answer should be A. Anyway, let's see maybe a little bit details. Maybe we'll see to break it. So choice A says for all x p of x or for all x q of x implies for all x p of x or q of x, right? So we need to have true implies false, right? So let's assume our domain has two elements, 1 and 2. So P of 1 would be, for example, let's assume it is true. Then P of 2, I cannot make both true because I need to have false here, right? So let me make it false. Similarly, um, Q of 1, maybe the first one I will make it true, and second one Q of 2 I will make it false. Now if you see the left hand side, sorry, if you see the right hand side, we have P of 1 or Q of 1, that is true. The next P of 2 or Q of 2, that is false. So the right hand side is now false. Now let's see the left hand side. We had to make it true, right? Now if you see for all x P of x, for all x P of x, see, we have false as well as for all x Q of x, that's also false, right? So you cannot basically make this side true if you want to make the right side false. So you cannot make a truth assignment since that true implies false. So A should be a valid statement. Now let's see the choice B. It says there exists an x, right? P of x, and there exists an x, Q of x. So it basically says the exception x, okay, p of x. So if your domain is having s1 or s1 and s2, it doesn't mean that both x should be same. Okay, these are independent statement. Okay, remember that implies the existence x, p of x, and q of x. Okay, so we want to make it is true implies false, right? So I can make, for example, let's assume the domain is 1 and 2. I can say that p of 1 is true and p of 2 is false. Here I can say p of, sorry, q of 1 is equal to false and q of 2 is equal to true, right? So there exists an x, p of x and q of x, true and false. False and true will be evaluating to false, but there exists an x, p of x. This will be evaluating to true, right? The exists x, q of x. This will be evaluating to true. So we have true implies false. So that means b is not valid. Similarly, if you see C, it says there exists an x, p of x or q of x. Here the both x are same, okay, implies for all x, p of x or for all x, q of x. This is very straightforward. We know that this statement should not be a tautology, right? We cannot guarantee that there exists a p of x and q of x. That means for all x, p of x or for all x, q of x is true, right? Anyway, let's see. True implies false, right? So for all x, p of x should be false. So I can say maybe I will take p of 1 is equal to true and p of 2 is equal to false. Here q of 1 is equal to true and q of 2 is equal to false. See, you have to take a truth assignment such that you are able to get true implies false. Okay, for all x, p of x, for all x, p of x is false. For all x, q of x, that's also false. So I have false here. Now if you see the exists an x, p of x or q of x, that is true because p of 1 and q of 1 evaluates to true, right? So that means C is also not valid. Now let's see the choice D that says there exists an x, p of x or q of x. I think here it is not all x, p of x. I think the question is having some mistakes here. So maybe I don't need to proceed. I think here there's some mistake here. Okay. So anyway, the answer should be A. Okay. Consider the following first order logic formula in which R is a binary relation. Okay. So we have the predicate here for all x or y. R of xy implies R of yx. So what is this relation? This relation says the given relation should be symmetric. Right? So this predicate will be true if the given relation is symmetric, right? Otherwise, it will be false. So I cannot say that this predicate is always true, right? But it is satisfiable. That means there exists some relation for which this predicate evaluates to true. So I can say that this predicate will be satisfiable. Now, if you see the question, it says talking about its negation also. So what is the negation of this? So if a relation, this says the relation should be symmetric. So the negation should be saying the relation should be non-symmetric, right? Or if you really want, you can take the negation of this. So that will be equal to the exists an x, the exists a y, right? It is not the case that if r of xy is present, then r of yx is present. It is not the case, okay? Or if you want, you can again um, take the complement inside, so that there exists an x, there exists a y, right? And r of x comma y implies r of y comma x means that is equal to r of x comma y complement plus r of y comma x, right? So I can write as there exists an x, there exists a y, r of x comma y, and not r of y comma x. So there exists a pair such that r of x comma y is present and r of y comma x is not present. So that type of relation is called non-symmetric. So there may be some relation that is non-symmetric, but all relations are not non-symmetric. So this predicate also will not be evaluating to true always, right? So both are satisfiable, but both are not valid. So the option B is correct. It says this predicate is satisfiable, and so is its negation. Okay, so the answer should be B. Which of the following is a valid first order formula? Okay, here alpha and beta are first order formula with x as their only free variable. Okay. So that means the value of alpha depends on the value of x, right? So alpha can evaluate to true or false depending on the value of x. So when we write this alpha, it really means our usual notation of alpha of x. Okay. Now let's see the first choice A. So we have for all x, alpha of x implies for all x beta of x, right? See the brackets, implies for all x alpha of x implies beta of x. Okay. Now, if this is not a tautology, then I should be able to have a truth assignment that true implies false, right? So let me take the domain as 1 comma 2. So I need to have this side false. That means I need to have some truth assignments that alpha of x is true and beta of x is false, right? Then only this side I will be able to get false. So let me take alpha of 1 is equal to true and beta of 1 is equal to false. So you can have alpha of 2 is equal to true and beta of 2 is equal to true. That's fine. But at least you need to have one assignment that true implies false, right? Now the left side is false. So if you see now the right side is false. Now you have to make the left side true, right? So if you see this statement for all x beta of x, that's already false, right? So this side is false. So we need to have for all x alpha of x should be false, right? Then only you can have this value as true. So I cannot change this. All x beta of x is always false, right? Now I had to make this side false. Now if you say this truth assignment, whatever we took, basically for all x alpha of x is basically, sorry, if you see our truth assignment, all x alpha of x is true. So our truth assignment is maybe we had to change. So let me change alpha of 2 is equal to false. Okay. If I change alpha of 2 is equal to false, still the right hand side still will be false because I have true implies false, right? But alpha of all x alpha of x is now false because I have true and false. And for all x beta of x is also false. So the left hand side is true and right hand side is false. So that means I have a truth assignment which evaluates to true implies false. So choice A is wrong. Now let's see choice B. So it's very straightforward question. It says for all x alpha, remember it is alpha of x, implies there exists an x alpha and beta. See, I can make this side true and this side false very fast because I can assume all the alpha of x is true, and if I make all the beta of x is false, then I will have definitely true implies false, right? Because here alpha and beta. Okay, so let me see the choice C. It says for all x alpha or beta implies there exists an alpha, right? All this implies for all x alpha. Okay, so I need to have true implies false, right? True implies false. That means for all x alpha should be false. Okay, so if I have domain 1 and 2, I can say alpha of 1 should be false and alpha of 2 I can take it as true. Then this is okay, right? This right hand side will be false. Now if you see the left hand side, I had to make it as true, right? So there exists an alpha. Since I took alpha of 2 is equal to true, see I could have taken alpha of 2 is equal to false. But anyway, let's see with this assignment. alpha of 2 is equal to true. So that means there exists an alpha that is true, right? So I have to make the left hand side of this condition should be true, right? Because 2 implies 2 should be will evaluates to true, right? So this side should be true. So already I took alpha of 1 is equal to false, so I can take beta of 1 is equal to true. So now for all x, alpha of x or beta of x, alpha of x or beta of x will be true. Right here, whatever value of beta, it will be true. So I am now having the left hand side also true. Right. So I have a truth assignment such that true implies false. So that means choice C is also wrong. So the correct option should be D. You can verify it with some domains to make sure that you are not having a truth assignment of true implies false. Which of the following first order formula is logically valid? Here alpha of x is a first order formula with x as the free variable. That means the uh, the truth value of alpha of x is going to be determined by the value of x, and beta is a first order formula with no free variables. That means the truth value of beta is going to be a constant. That means either it may be true or false. It does not depend on any variable. Okay, so beta may be either true or false. Okay, so let's see the choice A. It says beta implies there exists an x, alpha of x implies for all x, beta implies alpha of x, right? So we can say that this is not valid if we can have a truth assignment such that this side we should be able to evaluate to true, and the right hand side we should be able to evaluate to false. This right hand side will be false only if you have beta is equal to true, and the right hand side alpha of x is false. So that means at least one alpha of x should be false, right? At least one alpha of x should be false to say that for all x beta gives alpha of x is false, right? So I can have a truth assignment something like alpha of 1 is true and alpha of 2 is equal to false. So if I have this truth assignment, then I can say that the right hand side is false. Now if you see the left hand side, beta is already, we took it as true, right? This side is true. So this also should be true, right? So if you see our assignments, there exists an alpha of x. I took alpha of 1 is equal to true. So this is also going to evaluate as true. So we have true implies false, right? So that means A is not valid. Now let's see the choice B. It says there exists a beta, there exists an x such that beta implies alpha of x implies beta implies for all x alpha of x, right? That means I need to have a truth assignment such that true implies false. So this side should be false. That means beta should be true. And all x alpha x should be false. So let me have alpha 1 is equal to true and alpha 2 is equal to false, right? So beta is true. So there exists an x. Beta implies alpha of x. That's also true because alpha 1 is true. So we have true implies false, right? So B is not valid. Now let's see the choice C. We have there exists an x, alpha of x implies beta. Then we have for all x, alpha of x implies beta, right? So to prove this is not valid, I have to have a truth assignment such that true implies false, right? So here it should be true implies false, right? So beta should be false. So I know that beta should be false, and here also it is false. So I had to basically make for all x alpha is equal to true here, right? For all x, alpha of x implies beta, right? So I had to make all x alpha is equal to true. So that means alpha of 1 should be equal to true and alpha of 2 should be equal to true. Okay. So here beta is false, right? So I had to make this statement false so that I will have false implies false, that is true, right? So to make this left hand side true, I had to make their existence alpha of x is equal to false. But we know already that for all x alpha of x is true, so I cannot make their existence alpha of x false, right? So that means I cannot have a truth assignment such that true implies false, right? Now let's see the choice D. So the answer should be C. We can continue to prove that D is invalid. For example, here we have for all x, alpha of x implies beta, implies for all x, alpha of x implies beta, right? So I had to have a truth assignment such that true implies false. So that means beta should be false. And here I need to have at least one alpha that is evaluated true, right? So I can have alpha of 1 is equal to true and alpha of 2 is equal to false, right? Now if you see this statement will evaluate to false because alpha of 1 is true and beta is false. Now if you see here, I know that beta is false, right? So I had to make for all x f of x, sorry, for all x alpha of x should be evaluated to false, right? So false implies false will be true, right? So I have alpha of 1 is equal to true and alpha of 2 is equal to false. That means for all x alpha of x is false, right? So false implies false will be true. So I have a truth assignment such that I can get true implies false. So choice D is also wrong. So the correct option should be C. Which one of the following well-formed formula is a tautology, right? Or it's valid. So we can easily find out that the answer C is true because if you see the left hand side and right hand side, we have the same expression, right? So because we know that A implies B is equal to A bar plus B, right? So if you see P of xy implies R of xy is equal to not P of xy or R of xy. So answer should be C. Okay. Let's see the other choices. So if you see the choice A, I think we all know that these two expressions are not equal, right? So we have a by implication. That means if the left hand side is true, right hand side also should be true. If the left hand side is false, the right hand side also should be false, right? So for all x there exists a y, r of xy is basically says that for all x there exists a y, right? So if you assume we have a domain of 1, 2, 3. So if you take the pairs like this 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. The left hand side says for all x. So this is, let's assume this is x and this is y. Then for all x there exists a y, right? So that means in this row there should be at least one value that is evaluated to true, and similarly in the second row there should be at least one value that should be evaluated to true, and also in third row there should be one value that should be evaluated to true. And the second statement says the right hand side, if you see the right hand side, it says there exists a y for all x, right? So that means you are fixing the y, then you are saying for all x r of xy is true. That means all this column, all these values in this column, or all these values in this column, or all the values in this column should be true. At least one value, at least one column, all the values should be true, right? So these both are not equal. So choice A is wrong. Now if you see the choice B, it's very easy because you have r of xy here, and you don't have r of xy in the right hand side, right? So you have to make basically true implies false, right? Right. If you assume all the r of xy are false, then definitely this side will be true, right? So similarly, you can make the right hand side false by just taking all the s of x comma y is equal to false. Then the right hand side you have false, right? And left hand side you have true. So true implies false, right? So that means choice B is wrong. Now let's see the choice D. It is interesting because so far we have proved a predicate is invalid by considering only one domain. So if you take only one domain, this statement is always true. But uh, as we know that the a predicate is valid if it is true for all the domains, for all the interpretations. So I can have x a domain and y a different domain. So let's consider x and y are different domains. Then, for example, I can have x is equal to a set of boys and let y is equal to set of girls, and the predicate x comma y, p of x comma y may be x loves y. So this statement says all boys loves all girls, right? And the right hand side says all girls loves all boys. That is not true, right? So if I can say all boys loves all girls, that doesn't mean that all girls loves all boys, right? So choice D is wrong. So remember that we can even have different domains. Suppose U is the power set of the set S. For any t element of U, let the cardinality of t denote the number of elements in t, and t dash denote the complement of t. Okay. Now it's given that for any t comma r element of U, let t by r. So what is t by r? Be the set of all elements in t which are not in R. That means it's equal to t minus, right? So we know that t minus r is t intersection r bar, right? Now if you see the choice D, it's given that for all x element of U and for all y element of U, that means if you take any two sets from U, x by y is equal to y bar by x bar, right? What is x by y? That is x minus y, that's equal to x intersection y bar, right? Now what is y bar by x bar? That will be y bar minus x bar. So that will be equal to y bar intersection x, right? So these two are equal. So that is what the predicate says. So answer should be D. Which one of the following well-formed formula in predicate calculus is not valid? So we have to find out the not valid predicate, right? So we can easily see that the choice D is not valid. Here it says for all x, p of x or q of x. If this is true, then for all x p of x or for all x q of x is true. That's what the statement says. This is, we can easily prove that this is wrong. For example, I can have p of x1 is equal to true and q of x1 is equal to false, and p of x2 is equal to false, and q of x2 is equal to true, right? Now I can have for all x p of x, that will be false, for all x q of x, that also will be false. So the right hand side I will be having false, right? And if you see the left hand side, it says for all x p of x or q of x, so that will be true, right? So I have true implies false, so that means choice D is wrong. So we have to find which one of the following is not valid. So it clearly says that choice D is wrong. Now if you want, you can see choice C says there exists an x, p of x and q of x. That means there exists some x for which P of x and Q of x are true. If that is true, then there exists a P of x that it should be true, right? Because here it is true, that means some x, for example, x1, if I take x1, so P of x1 and Q of x1 both should be true here. If that is true, then there exists a P of x should be true, and there exists an x Q of x should be true, right? So this is a valid statement. Similarly, if you see the choice B, you can see that it says there exists an P of x or there exists an x Q of x. That implies the exists x p of x or q of x should be true, right? So this is also true. Now let's see A. I'm not spending much time here because I think it's very easy to solve. Now let's see the choice A. It says for all x p of x implies for all x q of x, right? If this is true, then the exists an x not p of x or for all x q of x. Okay, so if I want to make this as invalid, I need to have a truth assignment such that true implies false, right? So let's assume the left hand side is false. Okay, so that means there exists not p of x, that is false. That means for all x p of x is equal to true, right? Now for all x q of x, this should be false, right? So that means I can, if there is exists at least one p of q of x which is not true, then all x q of x will be false, right? So I can say that, for example, q of x1 is equal to false and q of x2 is equal to true. Okay. Now I had to make, so this left hand side is, sorry, now this right hand side is false. Okay, remember for all x p of x is true, and I took q of x such that one is false and another is true. Okay, I can even make all q of x is false, but let's see whether I can able to prove true implies false. Now I know for all x p of x is true, for all x p of x, for all x p of x is true, right? So this is true. So now to make this entire statement as true, this side should be true, right? But it says for all x q of x should be true, right? But we have already taken that for all x q of x is false. So that means here you will not be able to make left hand side true, right? That should be false, right? So you don't have a truth assignment to say that the left hand side is true and the right hand side is false, right? So A is also true. So which of the following predicate calculus is not valid? The choice D is not valid. Consider the first order logic sentence. F for all x there exists a y r of xy. Assuming non-empty logical domains, which of the following sentences below are implied by F? Okay, so the question is for all x there exists a y r of xy, right? Implies what should be in the right side. Okay, now if you see the choices, I have 4 here, right? So maybe I can see whether 4 is valid, then I can remove C and D. If you see the choice 4, it says not, so I can take the not inside here, so that will be for all x. Then I can take the not again here, so that will be there exists a y. Then these two knots can be cancelled out, so I'll be getting r of xy, right? So basically this statement and this statement are same, so I can write this implies this, that is true, right? So 4 is true, so that means the answer should be A or B, right? Now I had to see the first one is valid. So it says for all x there exists a y, r of xy implies there exists a y, there exists an x, r of x comma y, right? Definitely this should be true. It says for all x there exists a y, right? So this statement is true, then at least one pair of x and y should be true, right? See, if you consider it as a row, and okay, so it says for all x there exists a y, so that means in this row at least one is true, in this row at least one is true, and in this row at least one is true, right? So here it says at least one pair should be true. So if the left hand side is true, I can say the right hand side is true, right? So the answer should be 1 and 4. Answer should be B. Consider the following formula and its two interpretations, I1 and I2. So we have a predicate formula here, alpha, and domain is given as a set of natural numbers. And we have the predicate P of x says x is a prime number, and Q of xy, that is y divides x. Now the second statement I2 says the same as I1, except that P of x is a predicate, it says x is a composite number. Which of the following statement is true? Okay. Now it's given that Q of xy, that is y divides x, right? So if you see this predicate, this one, Q of y comma y complement, because Q of y comma y divides y should be true, so not of Q of y comma y, that should be false. Right? So this is false. Now we have a by implication, that means uh, if this side also should be false, right? But we know that there are exist x and y such that x comma y is true, right? Or I can say that y comma y is true, right? So this is true, this can be true sometimes, but this is always false. So that means this portion, if this portion is false. Okay. Now we have again a by implication here that says this portion, this portion should be always false, right? If this is false, this portion always should be false. But let's assume p of x is a prime number. That means this portion is not always false, right? Or if you assume p of x is a composite number, this portion is not always false. So this portion sometimes can be true, right? So we have true by implication false, right? So we know that the entire portion here will be false, even if p of x is a prime number or p of x is a composite number. So we know that false implies anything, right, is equal to true, right? So that means this predicate evaluates true regardless of if p of x is prime number or p of x is a composite number, right? So both I1 and I2 satisfies alpha. So answer should be D. Which one of the following predicate formula is not logically valid? Note that W is a predicate formula without any free occurrence of X. That means W can be either true or false always, regardless of the value of X. Okay. Now we had to find out which one of the following is not logically valid. Right. Now if you see the choices C and D, if you see here the right hand side is same, right, and left hand side is different, so I assume that one of these should be false. Okay, so let's try the choice D. So we have there exists a p of x implies w, right? There exists an x, p of x implies w, and it's equal to for all x, p of x implies w. Okay, so let's take the domain has two values, maybe x1 and x2, and let's see what is for all x, p of x implies w, right? So we know that for all x, p of x implies w should be equal to p of x1 and p of x2 implies w, right? So this should be equal to p of x1 and p of x2 all bar plus w. So this should be equal to p of x1 complement right? Or P of x2 complement plus W, right? Okay, anyway, now let's see what is there exists P of x comma W. So there exists P of x implies W, right? So that should be equal to P of x1 implies W, or P of x2 implies W, right? So this will be equal to P of x1 bar plus W, or P of x2 bar plus W, right? So this is OR operation here. So we can say this should be equal to P of x1 bar plus P of x2 bar plus W, right? And we are having the same equation here, right? So that means these two are equal. So definitely C should not be the answer. Okay, so answer should be so definitely C should be invalid. So answer should be C. Anyway, let's see all other choices. So we have choice A. It says for all x or for all x P of x or W. So that will be equal to P of x1 or W, right? And P of x2 or W, right? If you have two variables x1 and x2, right? So that should be equal to P of x1 into P of x2, right? Plus W. For all x P of x or W, right? This is all x, right? So for all x P of x or W, right? So first choice is correct. Now let's see the second choice. It says there exists a x P of x and W, right? So that means P of x1 and W, right? There exists an x, right? So or P of x2 and W, right? So we can take W outside. So that will be equal to P of x1 or P of x2 and W, right? So that's equal to the existence x, P of x and W, right? So second one is also right. Now we are claiming that C is wrong. Let's see. Now we want to prove that the choice C is invalid, right? So that's equal to for all x, P of x implies W is equal to for all x, P of x implies W, right? So basically I have to say that if this side is true, I should be able to prove this side is false, or vice versa. I have to say this side is false and this side is true, right? The existential truth is same like this. Then I can say that these two are not equal. Okay. So if I take W is equal to true, then that means the right hand side always will be true, right? And also the left hand side also will be true, right? So I should be taking W is equal to false. To prove this, I have to take W is equal to false. So W is equal to false. Now I can say that for all x P of x, if it is true, right? If it is true, then I will have true implies false, and that is false, right? But let's take for all x P of x is equal to false. For all x P of x is equal to false. So false implies false will be true. So right hand side I have true. Okay. Now I had to prove that left hand side is false. Right. So I have taken for all x P of x is false. Right. So maybe I have two values p of x1 that's equal to false and p of x2 that's equal to true. Okay, so for all x p of x is false. False implies w is taken as false, so false implies false is true. So I have right hand side that is true. Now if you see the left hand side, so p of x1 that is false, false implies false is okay. Then p of x2 is true, true implies false, that is false, right? So the left hand side I have false and the right hand side I have true. So the choice C is wrong. You can even expand this P of X implies W. Whatever we tried for other choices, you can also follow that method to see that these two are not equal. Okay, so the answer is C. Consider the first order predicate formula. So we have some predicate formula here, and it's given that A bar B denotes A divides B, where A and B are integers. So the domain is integers. Consider the following sets. So we have these three sets and we had to find out which of the above sets satisfies phi, right? Now let's see the formula. It says for all x, right? Then the bracket starts. You have for all z divides x implies z equal to x or z equal to 1, right? So if this is true, then there exists a w greater than x, and for all z divides w, that means w is equal to z or z is equal to 1, right? So this is the predicate. So if this statement is true, right, then this statement also should be true, right? So we had to find out for this domain whether this predicate evaluates true. Okay, so if you assume always this portion is evaluated to false, let's assume always this portion is evaluated to false, then there is no issues, right? All the domains will evaluate true, right? If this left hand side always evaluates to false. Is it the case that it always evaluates false? No, sometimes it evaluates true, right? For example, if you assume the value of x is equal to 4, so sometimes it is looping through the domains values, so it will reach the value 4. Now what it says is that for all z, if z divides x, so you are starting from 1 to maybe some point, and for all z you are taking the first value of z, z will be 1, so z divides x, that is true. Then it says that z is equal to x or z is equal to 1, that is true, z is equal to 1. Now if I take z is equal to 2, then z divides x, that is true, because 2 divides 4, that is true. Then that implies z equal to x or z is equal to 1, that is not true. Here z value is 2, right? So for x is equal to 4, basically this expression evaluates to false, right? So false implies anything is true. But for example, x is equal to 5, x is equal to 5, this expression evaluates true, okay? Because the value of z will be z is equal to 1 or z is equal to 5. Only in these two values we will have z divides x, and in that case z will be equal to x or z will be equal to 1. So basically what I am saying is this portion will evaluates true only if the value of x is prime, right, or x is 1. So if you just ignore 1, I can say that this evaluates true only when the given number is prime, right? So similarly here also this statement is same as this one. So here also it will evaluate true if the given number W, right? Here it is W. So W is prime, right? Here it is X. So here it says X is prime. Okay. So also there is one more condition here. It says there exists a W greater than X. So W is greater than X. So what this predicate is saying is that if X is prime in the domain, then in the same domain you have a W that is greater than X and W is a prime. Okay. So this is equivalent to the statement, if P is prime or if X is prime, then there exists a largest prime greater than x, right? If x is prime, there exists a largest prime that is greater than x. So if you see the set S1, right, this is not true for the S1, because if this is the condition, definitely the set should be infinite. So here the set is finite, so I can say that S1 is false and these two sets are infinite, right? So both these sets, this predicate will evaluate true. So S2 and S3 are true. The notation there exists, you can see an exclamation mark here, right? X p of x denote the proposition there exists a unique x such that p of x is true. Okay, so what it says is that this particular uh, syntax of predicate is true. For example, let's assume you're having a domain x1, x2, x3, and x4. So exactly one of these should be true. For example, if x2 is true, then all other value should be false, right? So p of x1 should be false and p of x3 should be false and p of x4 be false, p of x2 is true. Okay, so exactly one of this should be true. That is the meaning of unique x such that p of x is true. Okay, now if that is true, see here, if a unique x is true, that means there exists a p of x that is true, right? Because I can say if there is exists a unique x, that means at least one x is true. So the first one is true. Now, if there exists exactly one p of x that is true, then it is the case that for all x p of x is false, right? For all x p of x, this should be false, right? All x p of x should be false. So both statements are correct. So answer should be A. Let P of m comma n be the statement m divides n, where the universe of discourse for both the variables is a set of positive integers. That means m and n are positive integers. So m divides n means m can properly divide n. That's the meaning. Okay. Now determine the truth values of each of the propositions. Whether this predicate is always true for all n p of m comma n. That means every integer can be divided by every integer, right? So that is not true. So everyone knows this. This statement says there exists an m such that m can divide all n, right? So we have set of positive integers. Okay, 0 is not there, remember. So it's given that there exists an m such that for all n, m divides n. So that's true if you take m is equal to 1, that means 1 can divide every number, right? So the second statement is true, first statement is false. So answer should be C. The quantification, there exists an exclamation mark x p of x denotes, so this particular syntax denotes the proposition there exists a unique x such that p of x is true. Okay, so what it means is that if your domain has, for example, x1 and x2 and x3, for example, then if p of x1 is equal to true, then p of x2 and p of x3 both should be false. Okay, so exactly one of these should be true. Okay, then only this predicate should evaluate to true, otherwise it should evaluate to false. Now, can we represent the same predicate using the universal and extension quantifiers and logical operators? So it's sure that choice A is wrong. So it says there exists a P of X or, right? Or, see. So if this portion is true, this predicate is going to evaluate to true, right? So I can have an example. I can have P of X1 is equal to true, P of X2 is equal to true, and P of X3 is equal to false. This predicate is going to evaluate false for this because I have two truth values for X1 and X2, but the option A is going to evaluate it says true, right? Now if you see the choice B, this is also wrong because we have for all x p of x and, right? So if this is true, then only this predicate is going to evaluate as true, right? So if you see for this expression, it should evaluate as true, but for all x p of x will be false. So that means B is not the correct answer. Now if you see C and D, it says there exists an x p of x, right? That is true. There should exist an x p of x, that is true. And for all x all y, if p of x and p of y, that means if I am able to find two values p of x and p of y, if both are true, then that means x should be equal to y, right? That means x should be equal to y. Then I can say that there is exactly only one value for which p of x is true, right? So if you see p of x and p of y implies x is equal to y. Okay, so C is correct. D is wrong because it says p of x or p of y. So this is wrong, right? So correct option should be C. Let q of xy denote x plus y equals 0. And there will be two quantifiers. So the first one says there exists a y for all x q of x comma y is equal to 0. So that means basically you can say that for example there exists a y, right, for all x. So basically you can say that that's equal to uh, q of, let's assume you have x1 x2 x3 etc xn. So x1 comma y, right, and q of x2 comma y, these are all true, right? Q of x3 comma y, right? So that's a y, so y is fixed. Okay, now for various values of x, we are saying x plus y is equal to 0, right? So that is not true, right? Because if x plus y is equal to 0, so the value of y should be equal to minus x, right? Otherwise, it will not be equal to 0. So you cannot say that there exists a single y for all these x's, x plus y will values to 0, right? So first choice is wrong. Now the second choice says for all x there exists a y. So that means for all x you take x1, right? Then you can get some value for y, that's there exists a y, some value of y such that x plus y is equal to 0, right? So that value should be minus x, right? So the second statement is true, but the first statement is false. So answer should be B. So I think this question is a repetition question. So it's given that p of m comma n means m divides n, right? Now we have to find out which of the following predicate is true, right? So we know that this statement, this is false. This we already know that it says that for every m divides every n, right? That is wrong. There exists an m for all n, p of m comma n. This is true when we can have a value m is equal to 1, right? This two we have seen already. Now we have another predicate here that says for all n, p of 1 comma n. This is true, right? Because for whatever value of n, 1 divides n. That is true. So this statement is true. So 1 and 2 are true, and third is false, right? So answer should be A.